Now let's start. Hello everyone. We are Group Train, and our topic is game theory. So what is game theory? Game theory is, you can see it yourself, and I'm going to go through the basic part very quickly, as they are really basic compared to the later part. A game, informally, consists of players, actions, strategies, and payoffs. What is the difference between actions and strategies? Uh, we can consider rock paper scissors. Rock is an action in the game, and I choose rock is a strategy. It is a pure strategy game, and we'll talk about pure or mixed strategies later. Well, now let's look at different types of games. In a non-cooperative game, players only consider maximize themselves total payoff, and the major part of our project is on non-cooperative games. Zero-sum or non-zero-sum games. In each entry in the payoff matrix, if all the values in the entry add up to a constant, then the game is called constant sum. Zero sum is equivalent to constant sum, as we can do some strategically equivalent transformations on the payoff matrix. You'll see them later. Well, this is a zero sum game. And now comes the Nash equilibrium point. It's the focus of our project. And the definition of equilibrium point is, as an equilibrium point, a player cannot gain more only by changing his own strategy. So the player do not want to change, and so do other players. Well, what is important is how to find a Nash equilibrium point. Now let's consider let's consider the prisoner's dilemma. Sorry, my teammate made a mistake. It should be dilemma, not dilemma or something else. Let's consider prisoner's dilemma. For player A, if player B chooses confess, -8 is bigger than -10, so player A chooses confess. If player B chooses refuse, 0 is bigger than -1, so player A still chooses confess. Well, it's the same for player B, and we can underline -8, 0, -8, 0, and we can see that the entry -8, -8 is underlined, so it is a Nash equilibrium point, and the only Nash equilibrium point in this game. But when we consider the game rock paper scissors, we'll find that no Nash equilibrium point can be found by underlying method. So we have to allow mixed strategies, and players can play each action with non-negative possibilities. We use pi to denote the possibility for action I, and obviously, if a player chooses 1/3, 1/3, 1/3, 1/3, 1/3, his opponent cannot gain more by changing strategies. And when the opponent also chooses 1/3, 1/3, 1/3, Nash equilibrium point is achieved. Nash proves the existence of equilibrium points in finite mixed strategies games. Well, you can see it yourself. And the Kakutani fixed point theorem was used in his proof. We are not going to talk about it as it is too mathematical. So that's a basic part of our project. But let me introduce a method for some special cases first. Consider a game of two players. If player A can take a strategy such that for player B, whichever pure strategy he takes, his total expected payoff is unchanged. That means that player B cannot gain more by only changing his own strategy. Of course, he can neither gain less by changing in this case. And if B also takes strategies such that for player A, the expected payoff of each pure strategy is the same. A also cannot gain more by changing strategy. And then a Nash equilibrium is formed. To find such an equilibrium, we just need to solve two sets of equations. However, obviously this method is just for some special cases. Consider the payoff matrix for A. Obviously, the payoff for x1 and x2 can never be the same. Another special case is the zero-sum games. In zero-sum games, gaining more is equivalent to making the opponent gaining less, so we can find the equilibrium in another way. Again, consider a game of two players. If player A's strategy is fixed, then player B can always choose a pure strategy which gives the max payoff. So what player A needs to do is just to minimize the maximum of player B. And that leads to a set of inequations. By transforming them slightly, you can solve them by linear programming. Well, there are many methods for linear programming, but we are not going to introduce them here. These are two special cases, and we're going to introduce the general method later. Well, here comes the most important part, the general method for finding mixed Nash equilibrium of the many methods. The Lemke-Hausen algorithm is called the best way to solve bimatrix games. Bimatrix games are games of two players with finite possible actions. So let me introduce some concepts first. Labels. Player A has possible labels from 1 to n plus n. Player B also has possible labels from 1 to n plus n. And if I belongs to n, pi equals to 0 for player A, then player A has label I. If I belongs to n and action I for player B is one of the best pure strategies for B, then player A has label n plus I. Similar for B. So obviously at a Nash equilibrium, the labels that player A and B have are 1, 2, 2, 2, 3, 2, 2, 2, 2, n plus n. Polytopes. A set of inequations can be represented as a special shape, and the idea of going from vertex to vertex can help find many things. Consider the triangle formed by x greater than or equals to 0, y greater than or equal to 0, x plus y less than or equal to 1. The triangle has 3 vertices. This triangle is a polytope. Tailbox. By adding slack variables, we can transform in equations to equations, which makes life easier. See the example in this lecture note. Here, here, page, here. Originally, there are three equations. Y4 plus 3, Y5, smaller or equal than smaller than or equal to 1, and we add a slack variable R1 into that equation. So the equation becomes a new equation. This is a method of textbooks. And pivot operations. It means moving to an adjacent vertex. Different vertices satisfy different equations. Again, we take the triangle above as an example. 0, 0 satisfies x equals to 0 and y equals to 0. 0, 1 satisfies x equals to 0 and x plus 1 equals to 1. X plus y equals to 1, sorry. If a slack variable Si is said to be 0, then the equation containing Si is satisfied. For example, here, if R1 is 0, then y4 plus 3 y5 equals to 1. This equation is satisfied. If an original variable xi is said to be 0, then obviously xi equals to 0 is satisfied. Well, let's see the example of pivot operation, how it is operated. This is original. Textbooks. This is original textbooks for A and for B. The R1, R2, R3 are called bases, and these are non-basis variables. Here, x1 is brought into the basis, and S4 is transformed into non-basis. Obviously, when the Nash equilibrium is found, when the Nash equilibrium is found, those non-basis variables will be said to be 0, and we can get the value of basis variables. By these concepts, we can learn the Lemke-Hawthorne algorithm. We start from player A has labels 1 to n, and player B has labels n plus 1 to n plus n, which means that all possibilities for all the possible actions of A are 0. First, drop a label k from A and pick L, and drop L from B and pick L prime, and drop L prime from A and pick K prime, and drop and pick and drop and pick. If K prime equals to K, then a Nash equilibrium is found. About the mechanism, we are not going to talk about the mechanism here, as it is not so easy to show. So how to drop or pick? One drop and pick is just one pivot operation on polytope A or B. Or we can think about in another way. If player A drops label I, he adds the I's action to his strategy. If player A has label I, then the possibility for action I equals to 0. So if player A drops label I, he adds the I's action to his strategy. And then player A picks label J, which means that the action J for player B becomes one of the best actions for player B. And that's why player B needs to drop J, adding action J into his strategy. Well, by initially dropping different labels, the Lemke-Hawthorne algorithm can find at most n plus n different equilibrium points. But this method also has some limitations. The input has to be non-degenerate, which means that the number of best response actions has to be always smaller than or equal to the number of actions in the opponent's strategy. For example, if I use 3 actions to form a mixed strategy, your best response actions cannot exceed 3. So that's all about Lemke-Hawthorne algorithm, or maybe not all, but that's all we have done. That's all.